This video is approximately 50 minutes long, a sleep aid for late-night insomniacs. The entire universe is fleeing. Galaxies are moving away. Time is stretching out. Even the Earth beneath our feet is being carried along by the solar system, traveling through the Milky Way at a speed of 220 kilometers per second. And you are completely unaware. You are not standing still, but are being quietly pushed towards the end by the universe. We always thought the universe was static, just as we see it when we look up at the night sky. The stars hang obediently in the sky. The constellations do not change their shape. The moon rises from one direction and sets in another every day. Although the planets are a bit mischievous, after a while, they always return obediently to their original place. In the eyes of the ancients, all of this seemed so orderly. The sky was like a sacred scroll, hanging above the world. We were safe and sound on Earth, as if nothing would ever change. So people naturally assumed that the Earth must be the center of the universe, as solid as a rock. Everything else, like the sun, the stars, and the heavens, was revolving around us. You might think this is superstition, but this idea actually persisted for thousands of years. And it wasn't just because humans lacked imagination, but because it genuinely seemed reasonable. It explained the changing of the seasons, the occurrence of solar and lunar eclipses, and even the arrangement of celestial bodies. It gave us a sense of stability. The universe seemed like a well-oiled machine. Every gear moved in its proper place. Every star was in its designated position. There was not a hint of chaos, until one day, the seemingly perfect illusion began to crack. It started with Copernicus. He proposed a revolutionary idea. The Earth is not the center of the universe. Then Galileo, using his telescope, saw moons orbiting Jupiter. Next, Kepler discovered that planets do not move in circular orbits, but along an elliptical path, pulled forward by some kind of force. And so, little by little, the tranquility of the universe vanished, and we finally realized that we had misunderstood this world all along. Today, we know the universe is not a static picture at all. It is in motion everywhere, not just stars and stars, but entire galaxies, clusters, superclusters, and even space itself is expanding. The universe is not a calm ocean, but an ever-expanding wave. We are like a small boat, drifting on these waves, seemingly calm, but actually traveling through space-time at an astonishing speed. We stand on the Earth and feel that everything is stable. There is no wind, no vibration. The stars above our heads are not blurred into a streak. But this is just an illusion. It's simply because the scale is too vast, beyond the range our senses can perceive. In fact, at this very moment we are speaking, we are standing on a constantly rotating planet. This planet is racing around the sun, and the sun is carrying our entire solar system, speeding through the Milky Way. At the same time, it is being pulled by an invisible force, drifting towards the even more distant deep space. The old view of the universe has been left behind by time. What we see now is a universe concealing immense motion, and we have only just begun to try to understand the true meaning behind these movements. For a very long time, our understanding of the universe revolved around one fundamental point. The Earth is the center, and it is stationary. Everything else revolves around it. This wasn't just a simple idea. It was an entire system, an almost unshakable worldview. It was written into calendars, permeated religion, influenced the measurement of time, astrology, and even determined the way humanity viewed the world. And the creator of this system was named Ptolemy. Ptolemy lived in 2nd century Egypt. In Alexandria, it was an era where knowledge intertwined, and Eastern and Western wisdom merged. He was not just a philosopher, but also a mathematician and an astronomer. He wanted to interpret the sky with numbers, and depict the paths of the stars with geometry. He inherited the star catalogs of Babylon, the astronomical records of Egypt, and the geometric traditions of Greece. He compiled and organized all of these, and finally wrote the masterpiece that would dominate cosmology for over 1,000 years, the Almagest. In Ptolemy's model, the Earth is stationary at the very center of the universe. The heavens are like nested crystalline spheres, revolving around the Earth. All celestial bodies are fixed on these transparent spheres, circle after circle, from the moon to the most distant stars, forming a vast and orderly cosmic system. This system was not only beautiful to look at, but it also worked very well. It could explain the rising and setting of celestial bodies, the alternation of day and night, the changing of the seasons, and the patterns of solar and lunar eclipses. As long as you followed his mathematical logic, everything could be calculated. At the time, this was basically cutting-edge technology, but problems slowly began to emerge, especially with Mars, Jupiter, and Saturn. These slow-moving giants, they would sometimes exhibit an anomalous phenomenon in the sky. While moving forward, they would suddenly reverse course, as if backing up. In Ptolemy's theory of circular orbits, this made no sense at all. So, he had to add a small circle, having the planets orbit a small circle called an epicycle, while the small circle itself orbited a larger circle. In other words, he added a multi-layered system of circles for the planets. If that sounds complicated, you're right. It is complicated, but this wasn't to show off. It was to make the celestial motions mathematically coherent, but even so, it still wasn't enough to fit the observational data. So Ptolemy introduced another concept called the equant point, which was an imaginary point offset from the Earth, from which a planet's motion would appear to be uniform. It was with this complex yet precise model that Ptolemy's theory became the standard for over 1,000 years. It not only explained the heavens, but also satisfied humanity's psychological need for order and a center. Throughout the Middle Ages, it was revered as truth, accepted by the Church, and adopted by observatories across nations. But no theory can escape the test of time. Slowly, some astronomers began to feel that this system was too cumbersome. It was like trying to patch up an old machine. You keep adding gears, springs, and screws, but you can never figure out what's actually wrong with it. They began to wonder, what if it wasn't the sky revolving around us, but that we had misunderstood the entire structure of the world? Amidst such questioning, in the year 1543, a book that would completely overturn humanity's view of the universe was quietly published. Its name was On the Revolutions of the Heavenly Spheres. Its author was Copernicus. Copernicus did not initially set out to challenge Ptolemy. He studied law, medicine, and even understood economics. More importantly, he could read Greek and Latin, so he could understand the wisdom of the ancients. But none of these were his true passion. His true passion was the stars in the sky. He spent decades observing the heavens while contemplating the structure of the universe. His notes were filled with dense writing, and his mathematical models were layered one upon another. Finally, he reached a stunning conclusion, which is the core sentence of his book. The Earth is not the center of the universe. The Sun is. In his model, the Sun was placed at the very center of the universe. The Earth was just another planet, orbiting the Sun once a year, while also spinning on its own axis once a day. This rotation is what makes us see the stars rise in the east and set in the west. It gives us day and night. Copernicus also proposed a third motion. The Earth's axis is tilted, and the changes brought about by this tilt cause the changing of the seasons. This idea seems normal today, but back then, it was nearly fatal. He was challenging the entire religious and philosophical system, a belief in our centrality that had lasted for thousands of years. So he kept this theory hidden for decades. It was only in his old age, at the urging of friends, that he reluctantly published the book. Legend even has it that it was on his deathbed that he saw the first printed copy of his book, and then quietly passed away. Copernicus's theory, while conceptually a dramatic breakthrough, was not more accurate than Ptolemy's in its predictions. He still insisted that the paths of celestial bodies were perfect circles, and this was a major mistake, because the real universe never arranges its orbits according to human aesthetics. However, he lit the first spark, a spark powerful enough to burn down the entire old worldview. He opened a path for the later Galileo and Kepler, a path to the real universe. If Copernicus was the one who lit the spark, then Galileo was the one who fanned it into a flame. He didn't invent the telescope, but he turned the telescope into a breakthrough for human understanding of the cosmos. In 1609, an Italian professor named Galileo placed a strange device from Holland in front of him. It was a tube that, when its lenses were combined, could make distant objects appear closer. At first, it was just curiosity, but when he turned the telescope to the night sky, everything changed. The first thing he saw was the moon, supposedly a smooth, perfect, divine celestial body, but in his telescope, it was covered with craters and mountains, just like the terrain on Earth. He realized the moon was not perfect. It was a flawed world, just like ours. Next, he pointed his lens at Jupiter. He was astonished to find, for small points of light circling around Jupiter, he observed for many consecutive days. These small points of light were not stars, but moons orbiting Jupiter. This meant that not all celestial bodies revolve around the Earth. Jupiter had its own family of moons. This was another blow to the geocentric model. But the most crucial discovery was seeing the phases of Venus. Just like the moon, Venus was sometimes full, sometimes half, and sometimes like a small crescent. This could only be explained by the heliocentric model, because only when Venus moves between the Sun and the Earth would it exhibit these changes in brightness. These observations were not speculation, not theory. They were facts seen with his own eyes. This caused the foundation of the entire geocentric model to shake. Galileo saw a universe that overturned the old world through his telescope, but he couldn't precisely describe its laws with mathematics. That task was passed on to another astronomer. His name was Kepler. Kepler was an extremely persistent person. He didn't trust feelings. He only trusted numbers. He was a devout mathematician and an astronomer who was never content with the status quo. He did not originally support Copernicus's heliocentric theory, but fate pushed him into a key position. He became the assistant to Tycho Brahe. Tycho was the greatest observational master of his time. Without a telescope, he relied on huge instruments and incredible patience to manually record the planetary paths of almost the entire visible sky. Especially for Mars, the precision of the data was unprecedented. When Tycho passed away, this data was handed over to Kepler. It was as if Kepler had received the universe's codebook. He dove into it and spent 8 long years trying to fit the position of Mars to Copernicus's circular orbits. But Mars just wouldn't cooperate. It didn't follow a circular path. Sometimes it was fast, sometimes slow, sometimes it seemed to make a loop. Until one day, Kepler decided to stop forcing Mars to fit a circular orbit. He set aside philosophy, put his beliefs aside, and just listened to what the data had to say. And then he discovered the true rhythm of the universe. He proposed his 3 laws of planetary motion. First, the orbit of a planet around the Sun is not a circle, but an ellipse, with the Sun at one of the 2 foci of the ellipse. This perfectly explained the sometimes fast, sometimes slow trajectory of Mars. Second, a planet moves faster when it is closer to the Sun, and slower when it is farther away. If you draw a line connecting the Sun and a planet, then in equal intervals of time, the area swept out by this line is always the same. This is known as the law of equal areas. Third, he also discovered that the time it takes for a planet to orbit the Sun once, its period, squared, is proportional to the cube of its semi-major axis. This relationship allowed people, for the first time, to use a mathematical formula to predict the speed and position of planets. These 3 laws completely rewrote the foundations of astronomy. He no longer needed epicycles, deference, or equants, nor did he rely on the philosophical ideal of perfect circles. He relied only on solid observation and mathematical logic. Kepler described the rules of the universe with numbers. He didn't have a telescope like Galileo, nor the courage of Copernicus, but he connected their theories, and with mathematics, made the universe calculable, predictable, and understandable. He could not see the future, but he allowed the future to see the trajectory of the universe clearly. Sometimes, the simplest question can have the most profound impact. For example, why does an apple fall? This question led to one man. His name was Isaac Newton. He didn't observe planets with a telescope, nor did he handwrite tens of thousands of observational records, but he had a pen and a mind that could practically deconstruct the entire universe. Newton discovered that an apple falling from a tree wasn't just a law on Earth. He proposed that the Earth pulls the apple down because of something called gravity. And this force doesn't just exist on Earth. It's also present on the Moon, Mars, the Sun, and is everywhere, even between distant galaxies. He wrote this universal pulling force into a single formula, the law of universal gravitation. The meaning of the formula is simple. Between any two objects with mass, there is a mutual attraction. The force of attraction is proportional to their masses and inversely proportional to the square of the distance between them. In other words, the heavier the objects, the stronger the pull. The farther apart they are, the weaker the pull. This law solved a great, ancient puzzle. Why don't the planets fly away? And why don't they fall into the sun? Why does the moon keep circling the Earth? Why do you fall back to the ground when you jump, instead of floating off into space? The answer is gravity. And what's most stunning is that Newton used this law to not only explain motion on the ground, but also motion in the heavens. The sun's mass is large, so the Earth orbits around it. Mercury is closest to the sun, so it moves the fastest. At nearly 50 kilometers per second, Mars is a bit farther, so it moves slower. Everything fit his formula. Everything was logical. This was the first time in history that humanity used a single formula to simultaneously explain an apple on the ground and the planets in the sky. The universe was no longer chaotic. The starry sky was no longer mysterious. The trajectory of every star, every solar eclipse, every tide could be calculated in advance, down to the second, from Copernicus to Galileo to Kepler, and finally to Newton. The veil of the universe was lifted, layer by layer. For the first time, we possessed a set of tools that could completely explain the motions of the universe. Gravity became the greatest actor in the cosmos. Invisible yet powerful, universal yet precise. It kept everything in orbit, turned chaos into order, and transformed the universe into a solvable puzzle. But just when we thought we had explained everything, a new kind of motion began to quietly emerge. It was bigger, deeper, and more unexpected. It wasn't just about the motion of planets, but about our entire galaxy, the flow of the entire Milky Way. And the first person to realize this wasn't a physicist, but a musician. William Herschel was a German who moved to England to be a composer, but he became addicted to the starry sky. He composed music by day and ground lenses by night, building telescopes by hand. The telescopes he built were better than almost any on the market at the time. Much better. He used one to discover Uranus, but he didn't gaze at the sky to discover new celestial bodies. He had a bolder idea. He wanted to know if the sky had a structure. Was it chaotic and random, or was there some hidden pattern? So he decided to count the stars, literally count them, one by one. He selected a narrow region of the sky, like cutting a small slit in the night sky with a ruler, and then began to tally how many stars could be seen in that area. Then he would change direction, change the region, and continue counting. He and his sister, Caroline, counted countless stars using this method, and eventually pieced together a star map that wasn't drawn, but counted into existence. They discovered that the density of stars in certain directions was very high, and this coincided perfectly with that faint band of light in the night sky, the Milky Way. Based on this, Herschel drew a structural map of the Milky Way, a flat, disc-shaped region, with the greatest brightness at the center, and the sun located near the center. Of course, he underestimated the size of the Milky Way, because interstellar dust blocked the light from distant stars, but this map was still groundbreaking for its time. More importantly, he realized that the stars are not infinite. They are not just scattered lights sprinkled randomly across the universe. They form a system, a structure. We are not outside of it, but within it. This was the first time humanity stopped seeing the Milky Way as just a streak of light overhead, but rather treated it as a celestial structure with depth and a defined shape. Herschel called this system the Milky Way galaxy, but he didn't know at the time that the Milky Way was not the entire universe. It was just one island among many, and those faint, blurry nebulae were actually other galaxies, so far away we couldn't see their edges. Although he didn't see the whole truth, he took the crucial first step. He told us we are not at the center. We are in a structure. We are in motion. And the next question was, are we really moving? If the entire universe is in motion, how do we determine what is stationary and what is moving? This question requires us to think from a different perspective, the perspective of a frame of reference. Have you ever been on a train? When you look out the window and see another train slowly gliding past, for a moment, you can't tell if you're moving or if the other train is. This is the trap of a frame of reference. From inside your train car, everything seems stationary. The coffee is steady in your cup. Your book isn't floating away. But from the perspective of the platform, you are traveling at 80 kilometers per hour. Who is right and who is wrong? Both are right. Motion is relative. And when we observe the universe, we face the same problem. Our eyes, telescopes, and instruments are all on Earth. This planet is spinning and also orbiting the sun, and the sun might be moving too. So, are we moving or not? This was the very puzzle that the Dutch astronomer Kaptein set out to solve. He wasn't a loud person. He preferred quiet, and he preferred data. Most of all, he preferred telling stories with numbers. He didn't have his own large telescope, but he knew how to use observational data from all over the world to piece together a more complete picture than anyone else. He began a task that was extremely tedious, but profoundly important, measuring the positions of stars, their brightness, and their movement over time. Each year, the movement of stars across the sky is minuscule, perhaps just a fraction of an arc-second. But Kaptein didn't care. He took decades of accumulated data, organized it all, plotted it, and analyzed it. The drift patterns of individual stars began to emerge. He found that these drifts were not random. They showed a kind of collective flow, like ripples on the surface of the sea at night, one layer overlapping another. At first, he thought the stars were divided into two streams, one flowing this way and one that way. But later, he began to think about it differently. What if it wasn't the stars that were moving, but we ourselves? Then everything would make much more sense. It's like walking through a crowded square. The people around you seem to be flowing in all directions, but maybe it's actually you who is moving, and they are standing still. Kaptein performed the mathematical calculations, and sure enough, the conclusion was clear. The flow pattern of these stars could only be reasonably explained if the sun itself was also in motion. In other words, the sun is not stationary. It is drifting through the Milky Way at a speed of about 20 kilometers per second towards a point in the constellation Hercules. This was the first time we realized that the sun is also on a journey, not the anchor of the universe, but a fellow traveler. Kaptein wasn't satisfied. He wanted to know, if the sun is moving, then what is the structure of our entire Milky Way galaxy? He assumed the stars were uniformly distributed, and then, based on their brightness and distribution, he constructed a model a flat galactic disk, about 40 light-years in size, with the Sun located roughly near the center. This model became known as the Captain Universe, although we now know that he underestimated the true size of the Milky Way and ignored the obscuring effects of interstellar dust. At the time, it was the closest attempt to the truth. It made us, for the first time, truly see the Milky Way as a system to be understood, rather than just a hazy sea of stars. And as observational technology advanced, astronomers began to look even farther, towards those faint spiral nebulae. What were they? Were they also hurtling through space like the Milky Way? Were they in motion? In 1923, on Mount Wilson in California, an astronomer named Edwin Hubble pointed what was then the world's most powerful telescope at a faint patch of light in the night sky. It was the Andromeda Nebula. Many thought it was just a small structure within our own Milky Way, but Hubble thought otherwise. In that nebula, he found the crucial clue: Cepheid variable stars. This type of star has a special ability. They brighten and dim with a regular rhythm, and there is a formulaic relationship between this rhythm and their intrinsic brightness. If you know how bright a Cepheid variable should be, and then you see how dim it appears in the sky, you can calculate how far away it is. Hubble did the math, and the result was staggering. This nebula was too far away, so far that it couldn't possibly belong to the Milky Way. It was a complete galaxy in its own right, with its own stars, clusters, gas clouds, and possibly planetary systems. This meant that our Milky Way is not the entirety of the universe. It is just one island, and out there are countless other Andromedas, spread across the entire universe like scattered lights. Humanity's view of the cosmos was shattered once again. The world was far larger than we had ever imagined. But an even more shocking discovery was yet to come. Hubble continued to study more galaxies, measuring their distances, and also measuring their spectra. He found that the light from most galaxies was redshifted. What did this mean? It meant they were moving away from us. Even more astonishingly, the farther away a galaxy was, the faster it was receding, some at hundreds of kilometers per second, others at thousands of kilometers per second. It was like a grand feast of accelerated escape. This was the birth of Hubble's law. The universe is not static, nor is it revolving around us. It is expanding, and we are floating in this expanding bubble, carried along by the current. This was a major turning point in the history of science. It not only rewrote our view of the universe's structure, but also paved the way for the later Big Bang theory. But not all galaxies are running away. There is one exception: Andromeda. In 1912, the American astronomer Vesto Slipher used spectroscopy to measure Andromeda and found that its light was blue shifted. This meant it was moving towards us, not away. But at the time, no one knew how close it would get, whether it would pass us by or collide with us directly. The results confirmed that Andromeda is not just passing us, but is heading straight for us, and we are also moving towards it. This is a galactic-scale collision in the truest sense. However, this will not be a dramatic explosion of stars colliding with stars, because the space between stars in a galaxy is vast. The vast majority will pass each other by, rather than colliding head-on. What will be truly spectacular is the gravity. Gravity will distort the structure of the galaxies, stretching out their spiral arms, tearing apart gas clouds, and slowly pulling their cores towards each other. Eventually, the two galaxies will merge into one giant elliptical galaxy. If the Sun survives, we might find ourselves in a new orbit, circling the core of this new galaxy. This cosmic dance is set to begin in about 4-5 billion years, and we are just an insignificant speck of dust. In this gravitational ballet, the Milky Way appears like a silver ribbon scattered across the night sky, but we can't actually see its true shape from the outside, because we live inside it. It's like standing deep in a forest. You see trunks and leaves, but you can't see the outline of the entire forest. To see the Milky Way clearly, astronomers began to take a different path. They no longer relied solely on visible light, but used radio waves instead, because light is blocked by interstellar dust. But radio waves can penetrate these obstacles. They began to track a special signal, the 21 centimeter wavelength radiation from neutral hydrogen atoms. This is the most common element in the universe, and its faint emission is like the heartbeat of the Milky Way. By tracking these signals, astronomers discovered that the Milky Way is not a uniform blob. It has structure. It has spiral arms, a core, a halo, a certain thickness, and a rotation speed. They observed a class of cosmic beacons called masers. These signals come from gas clouds around newborn stars. They are bright and stable, making them excellent targets for tracking. Scientists tracked these masers for many years, recording their positions, proper motion, and their spectral redshift or blue shift. Finally, they pieced together an unprecedented 3D map of the Milky Way's motion. The results showed that the Milky Way does not rotate uniformly like a wheel. Some regions rotate faster, some slower. Stars spiral like snails. Gas clouds are torn apart. Star clusters are dragged along. The closer to the galactic center, the faster objects rotate. But the strangest thing is that the central region doesn't have nearly enough visible stars to account for its powerful gravity. This doesn't make sense unless there is a massive object that we cannot see. Scientists finally pinpointed this mysterious core, a small region in the direction of Sagittarius. It is exceptionally bright in the radio spectrum and is known as Sagittarius A. Its mass is 4,000,000 times that of the Sun, yet it is crammed into a space smaller than Mercury's orbit. This density is beyond what conventional physics can explain. It is not a star, not a star cluster. It is a black hole, a supermassive black hole. It says nothing, yet it dominates everything. Every star in the Milky Way, every star cluster, every gas cloud orbits around it. This is the gravitational heart of the Milky Way. It does not shine, but it is the anchor that keeps the entire system stable. And what's even more fascinating is that the Milky Way itself is not fixed. It's like a great dragon floating in the cosmic sea, itself tumbling, twisting, and swaying. The Orion Arm, where we are located, is not stationary either. It bobs up and down, as if riding waves of interstellar surf across the galactic plane. And this great dragon is being pulled by even more powerful tides, drifting towards a deeper, more hidden direction. That direction is the source of the entire cosmic dark flow, the path to our true destination. You're standing on the side of the road. A car whizzes by. The roar of the engine gets higher in pitch as it approaches, and lower as it moves away. This is the Doppler effect. Sound changes, and so does light. If a star or galaxy is moving towards us, the light waves it emits are compressed, shifting towards the blue end of the spectrum. This is called a blue shift. If it's moving away, the light waves are stretched, and the spectrum shifts towards the red end. This is a red shift. Scientists began using this method more than 100 years ago to measure the motion of galaxies. The results were stunning. Almost all galaxies are moving away from us. The farther away they are, the faster they flee. This is the core idea of Hubble's law. The universe is expanding, and this expansion is rhythmic and regular, like a balloon being inflated. Each galaxy is a small dot on the surface of the balloon. As the balloon expands, all the dots move away from each other. But there are exceptions. Andromeda is one of them. It is flying towards us, and not slowly, at 110 kilometers per second. But don't worry, it's 5 million light years away from us. Even at that speed, it will take over 4 billion years to collide. You might think this is the whole story of cosmic motion, but this is just the surface. There is a deeper force driving everything. Scientists discovered that galaxies are not just moving away from us with the expansion of the universe. They are also flowing, as a whole, in a specific direction, like a dark current in the cosmos. This isn't turbulence. but a coherent, large-scale flow, pointing towards a region we cannot see. This region is called the Great Attractor. The problem is, when our telescopes look in that direction, all we see is a wall of obscuration. The plane of the Milky Way, dense stars and dust, block our view. We can't directly see what is hidden behind it. But the motion of galaxies doesn't lie. Just as you can't see the wind, but you can see the leaves being blown. Scientists inferred from the speed and direction of galaxies that a powerful gravitational source exists, which is slowly pulling our entire local supercluster towards it. This region includes the Norma cluster and the even more massive structure behind it, the Shapley supercluster. It is one of the most massive concentrations in the known universe. We are drifting towards it at a speed of 600 kilometers per second. It's not in front of us, but it is changing our trajectory, like an invisible magnet, pulling the entire cosmic backdrop towards it. At the same time, scientists discovered something else that was shocking. This pulling is not one way. We are not just being attracted by something. We are also being pushed by something. They call it the dipole repeller. It's not a celestial body, but an extremely empty region of the universe, with almost no galaxies, no clusters, no sources of gravity. It is a cosmic void in the truest sense, because there's nothing there. There's nothing to pull us. The universe is like a river. On one side, a waterfall is pulling things in. On the other side is calm water, with no resistance. We are passively pulled towards the stronger side. Scientists used the Cosmic Flows project to track the motion of tens of thousands of galaxies, combining information like redshift, blue shift, and peculiar velocity. They created a flow map of the universe. This map shows that we are like travelers on an invisible cosmic river, flowing downstream, and the destination of this river is something we still can't say for sure. It's hidden behind the zone of obscuration, on the other side of the Milky Way, in the darkness, beyond the boundaries of our knowledge. But we are heading towards it, irresistibly, with no way to turn back. In 1998, something happened in the world of astronomy that left everyone completely stunned. At the time, scientists were conducting a study that sounded pretty ordinary. They wanted to know whether the expansion of the universe was speeding up or slowing down. The logic was simple. After the Big Bang, the universe began to expand, but gravity was always pulling everything back. So, the general consensus was that the rate of expansion should be gradually slowing down. And so, two research teams, one in the northern hemisphere and one in the southern, began simultaneously tracking a special type of star, Type A supernovae. This type of supernova is like a beacon in the universe. When it explodes, its brightness is almost always the same, so it can be used as a standard candle. If you know how bright it should be, and then see how dim it appears, you can calculate how far away it is. They collected data from dozens of supernovae in distant galaxies and made a graph with distance on the x-axis and redshift on the y-axis. When the results came in, everyone was speechless, because the data told them the universe was not slowing down, it was accelerating. In other words, the farther away the galaxies are, the faster they are fleeing. Instead of being slowed down by gravity, they were speeding up as if someone had stepped on the gas. This is impossible. No one had predicted this result. It completely shattered all our assumptions about the fate of the universe. To explain this acceleration, scientists proposed a new concept. Dark energy. We don't know what it is, and we can't directly observe it, but it must exist, because other than it, nothing else could be making the universe expand at an accelerating rate. Even more bizarrely, according to current calculations of energy distribution, about 68% of the energy in the universe is this dark energy, the matter we are familiar with. Stars, nebulae, galaxies, planets, including you, me, and this apple, make up less than 5% of the universe. Another 27% is another type of invisible matter that produces gravity, called dark matter. The rest, the vast majority, is this formless yet powerful dark energy. It doesn't pull things together like gravity. It's the opposite. It pushes things apart. It's the unseen hand stretching space further and further. It doesn't even weaken. It doesn't get diluted as the universe gets bigger. On the contrary, the more space there is, the stronger the dark energy becomes, because it is a property of space itself. It's like putting dough in an oven. The more the dough expands, the more dark energy is activated, pushing the dough to expand even faster. This is a positive feedback loop, an endless acceleration. Scientists tried to explain it with quantum theory. Perhaps dark energy is vacuum energy, the energy fluctuations that constantly pop in and out of existence at the quantum level in seemingly empty space. But the problem is, the math doesn't cooperate with the theory. The calculated value for dark energy is 120 orders of magnitude larger than the observed result. This is the most absurd discrepancy in the history of physics. It's like trying to calculate the weight of a grape and getting the mass of the entire Earth. In other words, we don't understand it at all. It is silent, yet it changes everything. It is tearing the universe apart from the inside out. An untouchable, yet ultimate force that rules the fate of the cosmos. And this leads to the next question. If dark energy continues to accelerate the expansion of the universe, where's the future of the universe heading? There isn't just one answer. We all know that all things have a beginning and an end. But when that end is applied to the entire universe, it's not just a final point, but a farewell in the truest sense. Since the discovery of dark energy, scientists have started to seriously consider a question. How will the universe end? The first and most extreme hypothesis is called the Big Rip. This model assumes that dark energy will not only continue to drive the universe's expansion, but its force will grow stronger and stronger. How strong? Strong enough to overcome everything, including the gravitational structures that were once stable. At first, galaxies are just pulled farther apart. Then, the galaxies themselves can't hold together. Stars begin to be pulled away. Planets are ripped from their orbits. Even the distance between atoms will be torn apart. Finally, even the quarks that make up protons will be unbound. In the final moments of the Big Rip, all particles will be stretched into cosmic strings, from which there is no return. Time and space themselves will rupture, and the universe will become an irreparable tear. It sounds terrifying, but there's another theory called the Big Freeze. It's less dramatic, but far more grim. This model suggests that dark energy won't get stronger. It will just remain constant, silently pulling the universe apart, bit by bit, like a show that never ends. But the audience just leaves. The theater lights dim slowly. The seats empty one by one. The sounds fade away. As the universe continues to expand, galaxies will move farther and farther apart, until they are too far to communicate even with light. You will no longer see other galaxies, only the lonely points of light within your own. After trillions of years, the fuel of stars will be exhausted. Red dwarfs will burn out one by one. Galaxies will become dead seas with no new stars being born, leaving only white dwarfs, neutron stars, and black holes, drifting slowly. Further on, even black holes will begin to slowly evaporate through Hawking radiation. This process could take a Google years. Eventually, all celestial bodies will vanish. The universe will be left with only cooled particles, with energy so diluted it's nearly zero. The temperature will drop to near absolute zero. There will be no reactions, no motion. It is a silent end. No explosion, no tearing, just a gradual, complete, and quiet disappearance. What's more interesting is that some theories suggest that even this big freeze is not the end. The universe, like a bubble in still water, might randomly spawn another bubble universe. That would be another beginning, another Big Bang. But that is beyond the scope of what we can observe. It belongs to the realm of philosophy and imagination. What we know now is that dark energy dominates the future. It does not shine, but it decides our fate. It hides in every inch of space. Like the breath of the universe, it is a push, an expansion, a constant farewell. And on this ever-expanding road, our Milky Way is not idle. It is being attracted, being pulled, drifting towards a deeper, more distant destination. That destination we cannot yet see clearly, but we know we are heading towards it. But one thing is certain, we are moving away from each other. The universe is not a static stage, but an ever-expanding theater. The lights are dimming. The stage is stretching. The actors are exiting. In the end, only one audience member will be left sitting there. That audience member might be the last particle to wink out of existence. It might be a lonely electron floating in the silence. Or perhaps it's the moment you and I look up at the starry sky in the dead of night. So don't be in a hurry to ask where the end is. And don't fear how cold the ending might be. Because your being here, being able to contemplate all of this on this tiny planet, is already a miracle in itself. It is the questioning of the universe that allows humanity, in the vastness, to see its own courage and light.